Hello students, welcome back. We're on to our next lesson. We're on notes number 53 and the title is Combinations. So I will pause while you're getting yourself ready. I'm looking out the window. I actually have a window in my classroom known as my spare bedroom. And today is just pouring down rain. At least the plants are getting some water. That's good. That reminds me of a joke. Do you know why plants hate math? Because it gives them square roots. Hardy har har. Thank you, Sophie, for laughing. Okay, so remember last time we learned about permutations, and we have the formula NPR, which is n factorial divided by n minus r factorial. It tells you the number of permutations of R objects taken from a group of n distinct objects, and we also could write it as, oops, wrong tool. We also could write it as this kind of notation or this kind of notation. I've seen all three. Okay. Remember also that we learned about permutations with repetition. We were looking specifically at words that have repeated letters, and we noticed that if you have repeated letters, then you have to divide by the number of repeats factorial. So for example, if you had the word, let's see, algebra, you have 7 letters, so you have 7 factorial ways to rearrange those letters. However, because you have 2 A's, you have to divide by 2 factorial because there are 2 factorial ways to rearrange those A's. And it doesn't matter what order the A's are in, right? Because an A is an A. So we don't want to have all those extras. Well, that leads us to today's concept. And we're going to start with a couple of examples. So, number 1, Mrs. Zimmers wants 3 students to help her find more math jokes. 1 student to search the internet, 1 student to look in library books, and 1 student to make up their own jokes. Any volunteers? Out of a group of 19 students, how many ways can students be chosen for these 3 positions? Okay, so in this problem, each position is unique. It's kind of like choosing 3 letters out of 19 letters where each letter is unique. They're distinct is another way to put it. So this would be a permutation type problem. And so we would have 19p3, and we can put that into a calculator. Remember your shortcut if you use the alpha menu. Alpha, window, and then number 7. I'm finding it right now, and I'm going to type the numbers in, and we get 5,814. Okay, now here's a related question, problem number 2. Mrs. Zimmers wants a team of 3 students to help her find more math jokes. Out of a group of 19 students, how many ways can students be chosen for this team? So notice that each of the 3 people does not have a specific role, and so it doesn't matter what order they're in. It doesn't matter who is who in that team of 3. And so when order doesn't matter, we are talking about combinations instead of permutations. So what we can do is take the answer that we got to the previous problem, which was 5,814, and divide it by the number of ways that we could be rearranging those 3 students, which is 3 factorial. So if you think about it, what we just did then is we took 19 factorial and divided it by 19 minus 3 factorial, which was the permutation part, and also divided it by 3 factorial, which takes out all of the repeats of rearranging those 3 people. So that leads us to our combination formula. So for combinations, we have NCR, but we often say N choose R. So N choose R is N factorial divided by N minus R factorial times R factorial. So that extra R factorial in the denominator is getting rid of all of those repeated arrangements of the same things. Important key to remember, is that for permutations, order matters, and for combinations, order doesn't matter. All right, so we're going to find each of the following combinations. We're going to do it first without a calculator, just using the formula. And then secondly, I want you to find your combination button on your calculator and give it a try. So we have 3 choose 0. That would be 3 factorial divided by 3 minus 0 factorial times 0 factorial. Nope. What am I doing? Yeah, that's right. Just doubted myself there for a second. Okay. So this is equivalent to 3 factorial divided by 3 factorial, 0 factorial. And 3 factorial divided by 3 factorial is 1. And we have previously defined 0 factorial as 1 as well. And you can see why. Because if you think about it, it's like, okay, there are 3 people, I have to choose none of them. Or there are 3 pizza toppings available, I choose none of them. I choose 0. I don't want any toppings on my pizza. How many ways are there to do that? There's one way, you just don't do it. Not doing something is considered a way of doing something. And so we end up with just 1 here. How about 3 choose 1? We have 3 factorial over 3 minus 1 factorial times 1 factorial. So we have 3 factorial over 2 factorial times 1 factorial. We know 1 factorial is 1, and we know that 3 factorial is the same as 3 times 2 factorial. So we can cancel the 2 factorials. And all we have is 3 divided by 1, so our answer is 3. How about 3 choose 2? So we have 3 factorial divided by 3 minus 2 factorial times 2 factorial. And that is going to be 3 factorial divided by 1 factorial divided by 2 factorial. Notice that that's exactly the same as a previous one, because choosing one thing out of 3 is exactly the same as not choosing 2 things out of 3. So we have a lot of symmetry going on here. If there are 3 things available, if there are 3 pizza toppings available, mushrooms, green peppers, and olives, you can either say, I choose mushrooms, you've chosen 1, or you can say, I don't choose green peppers and olives, and you've not chosen 2. They're going to be the same thing. So we end up with 3 again. And 3 choose 3. Guess what? Choosing 3 things is exactly the same as not choosing, am I saying this right? Not choosing anything? Choosing 3 is the same as choosing 0 because you are not choosing nothing. Feel like I'm getting myself twisted around there. 3 factorial is 3 minus 3 factorial, or 3 choose 3 is 3 factorial over 3 minus 3 factorial times 3 factorial. Today is a tongue-tied kind of day, apparently. And so this is 3 factorial over 0 factorial 3 factorial. That is exactly like the first one. And that's also 1. So we have 1, 3, 3, and 1. Keep that in the back of your mind. That's coming up again in our next lesson. Okay, we're going to do some examples involving playing cards. And there's a lot you can do with playing cards. For one, you can play games with playing cards. Some people aren't that familiar with playing cards, so I'm going to take a minute to describe to you what you have in a standard deck of playing cards. You have 52 cards. 26 of them are red. 26 of them are black. They're divided into what we call suits. The designs are the suits, so you have hearts. There are 13 hearts. They're red. You have diamonds. There are 13 diamonds. They're red. You have clubs. 13 clubs. They're black. And you have spades. There are 13 spades. They are black. So you have an ace, which is your 1. They call it an ace. Usually it says A on it, not 1. And you have a jack, queen, and king in each suit, and the jacks, kings, and queens are known as face cards. They have faces on them. Okay, so those are the cards that make up a deck of cards. So now we're going to go through some examples and find the number of combinations for different questions. So let's say you're playing a card game and you get to have 5 cards in your hand. Well, this is a combinations problem, not a permutations problem, because it doesn't matter what order you hold those cards. I do play a game where it does matter what order you hold those cards. Have any of you played Bonanza? It's the game about planting beans in your bean farm. My family likes that game. And you do have to hold your cards in a particular order. But in general, when you're playing with a standard deck of cards and playing a typical card game with 5 cards in your hand, it doesn't matter what order they're in. Okay, find the number of possible 5-card hands that contain 5 red cards. So what we're saying is all 5 of your cards are red. So to figure this out, you say to yourself, how many cards are red? 26. And how many do I have? 5. So this is going to be 26, choose 5. And then you can compute that number. Should have done that ahead of time. 26, choose 5 is 65,780. There are 65,780 different hands that would consist of 5 red cards. Part B. Find the number of possible 5-card hands that contain 2 jacks and 3 cards that are not jacks. Okay, notice we have the word and if you think back to our lesson on counting, when you have and, you multiply. It's like wearing a pair of jeans and a t-shirt and a sweatshirt. Remember, we multiplied, and that was the fundamental counting principle. So we have 2 jacks and 3 cards that are not jacks. How many ways are there to get 2 jacks? Well, how many jacks are there in the deck? There are 4 jacks in the deck. How many are you getting? You're getting 2. So this is 4, choose 2. Times, for the and, now 3 cards that are not jacks. How many non-jacks are in the deck? Well, there were 4 jacks in the deck. There are 52 cards in the deck. That means 48 cards are not jacks. So there are 48 non-jacks available, and how many are you getting? You're getting 3. Okay, so when we compute those, the first combination gives us 6, and the second combination gives us 17,296, and when you multiply those, you get 103,776. Okay, let's do a couple more. Find the number of possible 5-card hands that contain 5 clubs or 5 diamonds. Do you remember from the day we did the counting, when we have or, we just add. We don't multiply, we add. Like if you wear a t-shirt or a sweatshirt, you're not going to be multiplying those together. You're just going to add the number of ways to choose a t-shirt to the number of ways to choose a sweatshirt. So how many ways could we get 5 clubs? So you ask yourself, how many clubs are there? And the answer is 13. And how many am I choosing? I'm choosing 5. Plus, now for 5 diamonds, you ask yourself, how many diamonds are there? There are 13 diamonds. And how many am I choosing? I'm choosing 5. Okay, 13 choose 5 plus 13 choose 5. And what is 13 choose 5? It is 1,287. Multiply that by 2. And we get 2,574. Okay, and now again, 5-card hand, we are going to have at least 3 spades. When you have one that says at least or at most, you have to really stop and think it through. It's a little bit more complicated. So if you're getting at least 3 spades, that means you're getting 3 spades or 4 spades or 5 spades. We stop there because you're only getting 5 cards altogether. So because of or, we're going to be adding 3 things. Now, when you get 3 spades, remember, you still have 5 cards altogether. So 3 spades doesn't just mean 3 spades. 3 spades means 3 spades and 2 non-spades. And then 4 spades doesn't just mean 4 spades, it means 4 spades and 1 non-spade. Some of these spades are a little pathetic. And then we have or, and then when you get 5 spades, well, that does just mean 5 spades because you're only getting 5 cards, so you don't get anything else. Okay, so how many ways are there for this to happen? So 3 spades. Well, how many spades are there? 13. How many do you get? 3. And times 2 non-spades. How many non-spades are there? Let's see, there's 52 cards, 13 are spades, 39 are not spades. 39 non-spades, how many are you getting? You're getting 2. Plus 4 spades. There are 13 spades, how many are you getting? 4. Times 1 non-spade. There are 39 non-spades, how many are you getting? 1. Or, so plus 5 spades. There are 13 spades, how many are you getting? 5. Okay, so we're going to compute all of this. All right, so we compute all of these combinations. Now I want to ask you about one of them. Was anybody surprised that 39 choose 1 was 39? When you saw that, you probably went, oh yeah, I should have known that without even having to put that in my calculator because I have 39 cards to choose from. I'm choosing 1 card. How many ways are there to do that? 39 ways. That makes total sense. And now when we compute all of this, we end up with 240,942. All right, that is our lesson for today. And so when you do your homework, you're going to get to do some playing card problems and a few others. There are a couple where you get to choose whether it's a permutation problem or a combination problem. So remember, think about whether or not order matters. Check your answers, ask questions, and send pictures. Thank you, everybody. You're doing a great job.